is Rose Titcomb, and I'm the secretary for San Francisco CSHE. Unfortunately, our dear Angel can't be here today, but he is here in spirit. And I just wanted to go through the list of upcoming events, and I'll do it by date. You can also find this on the CSHE website, so no need to remember. So the next event is September 15, which is the 29th annual SoCal Seminar in Long Beach. And then our next presentation is September 20, and it's going to be on Legionella. And then we have our NorCal seminar. It's the 13th one in Fairfield. And finally, we have our Christmas party that Beth and I have been working on December 7th, and details will be coming out soon about that. And I just wanted to say, for the next presentation on September 20th, we are hoping to try to do an in-person. So we're actually looking for sponsors. So I don't know if it's at a hospital, if it's at a restaurant, but we're really open. We'd like to get everyone together if possible. Finally, we have Mark McGinn, and he's going to do a presentation today on steam quality and sterilization. So I will hand over the torch to him.
Thank you, Rose. Thank you all for inviting me here today. I'm going to share my screen, so if someone could let me know if this is working, that would be great.
Looks great.
Okay. Well, thank you so much again for inviting me. Today we're going to talk about steam quality and sterilization, and just a little brief plug. They told me I could plug myself and my company real quick. So my name is Mark McGinn. I've been in this industry for about 28 years. I'm the Western Regional Technical Manager for Watson McDaniel, and I'm based out of Southern California, by the way. We are a 144-year-old steam, condensate, and thermal fluids controls and instrumentation manufacturer based in Pottstown, Pennsylvania. All of our products are made here in the USA, and we're kind of a small company, but we have a lot of experience in the industry. Today, we're going to talk about steam quality and sterilization, specifically in the quality of steam and dryness, cleanliness, and just the overall product going into the sterilizer, and some best practices that we can all do to mitigate problems in the sterilizer. As a steam using industry, healthcare is one of the largest steam users in the nation because there's just so many hospitals and healthcare institutions out there. And typically they're using it for, HVAC purposes, for creating hot water, humidification. But sterilization is a key element to any institution that is running an operating room or using sterile instruments. And the interruption of this service can cause, delays and loss of revenue for a facility. Although it's for very large facilities, it may not be a problem because they have backup. But what we found over the past 28 years, what I found is that for smaller and mid-sized folks, the interruptions can be a major problem to a nuisance. So hopefully we're going to, by the end of today, give you some best practices that will help mitigate, but not completely eliminate some of the issues dealing with steam quality. So what is steam sterilization? Well, steam sterilization is achieved by exposing the items to be sterilized with saturated steam under pressure. And the steam enhances the ability of the heat to kill microorganisms by reducing the time and temperature required to denature or coagulate proteins in the microorganisms. So in most cases, plant steam is generated on site or by a utility and then piped at a higher pressure to the area where the steam sterilizers are located. In some cases, there are steam generators close to the steam sterilizers that will generate their own steam. But typically, where we find the issues with steam quality in dryness and cleanliness is the poor piping practices or missing components prior to the sterilizer. And in looking at best practices to improve quality and performance of the steam sterilizer, it has nothing to do with the sterilizer itself. The OEMs that produce the machines that do the work produce outstanding quality work, but it's generally what happens way upstream or prior to the sterilizers that affects its ability to produce good quality steam sterilization. I'll stop here just a minute. I'm not going to go too deeply into the specific standards. If you want to look at some standards in the future, if you're interested, there's the ANSI and AAMI, which is Association of Advancement of Medical Instrumentation, that ISO 17665 standard, or the European EN 285 standard, which will give you some better detail of some other areas. But I'm going to focus primarily on the steam quality aspect of what we're doing prior to the sterilizer. And incidentally, if you do have questions, I'm going to leave some time at the end where you can, we'll open it up a little bit. So please feel free to, at that point, to come back with your questions. So why do we use steam specifically? And I always like to start off with some basics here. And we're talking about saturated steam. And I'll differentiate saturated steam versus superheated steam. And superheated steam would have an additional sensible heat content, but saturated steam is has a direct relationship between pressure, temperature, total heat content, and then volume of that gas. And we're talking about the water molecule. So in the gaseous phase versus the liquid phase. We're not going to talk about the solid phase, but the water molecule, and let's kind of drill it down to 1 pound of water at 32 degrees has 0 BTUs. So if we add 1 BTU, we raise that temperature 1 degree Fahrenheit. And the addition of each BTU raises that water temperature by 1 degree until we reach 212 degrees. So that liquid at that temperature has 180 BTUs in that pound of water. For us to change the phase of that water to a gaseous state, we need to add 970 BTUs. So if you see on that 0 PSI line, that 212, it's got 180 BTUs in its sensible heat, that's the liquid phase, and then it has 970 BTUs in its gaseous state. So there's a 5-to-1 ratio of heat content in that gaseous phase of steam. So it's extremely efficient in transferring heat. In fact, that latent heat column is the heat that transfers off to a cooler, surface like a steam pipe or anything that's cooler than that, steam. And then when it does transfer the heat, it condenses back into liquid. It gives off that heat to the surface and then condenses back into liquid, or we call condensate. And that's how the system works. So it's very, very efficient. The nature of that water molecule in the saturated gaseous form really speeds up the sterilization process in denaturing the organisms that you're trying to get rid of. So in this regard, let's look at the steam vacuum process. That these are 5 typical steps for the whole cycle. And the first step is removal of air from the chamber. So the load gets packed, goes into the chamber, the door gets closed, they hit the button. First thing to do is remove the air from the chamber and the load. The next thing is they admit steam into the system, and it's basically, and I'll talk about how it's admitted into the system, but it's admitted into the chamber until sterilizing temperature is attained through the load. And then there's a dwell time where the temperature is maintained inside the system, and the sterilizing temperature is maintained inside for a specific period of time. That's generally predetermined by the manufacturer. Next is a drying process where the steam is removed from the chamber and the pressure reduced sufficiently to permit the evaporation of condensate from the load. And then finally, the vacuum break. The air is admitted back to the chamber through a bacteria retentive filter until the chamber reaches an atmospheric pressure. So I would like to go back to the second area, that's steam emission process. And typically what we see in a typical sterilizer is that you have a control valve, and that's what I'm going to circle here. This is just a typical on-off type of control valve on the steam supply. It's usually a solenoid, and when steam needs to be admitted into that process, the solenoid generally opens, allowing steam to enter the chamber. And when that system is closed, steam is obviously behind that solenoid valve. And as steam does, all it wants to do is give up its latent heat and condense back into water and liquid. So in a lot of cases, what we see on these systems is that the first thing that gets sent into the steam space is condensate, liquid condensate. And that's really, we don't want that in the system because it, that obviously doesn't have the heat content that the steam does, but also there's some other issues that we're going to talk about associated with liquid condensate entering the steam space. So we really want to make sure that we remove that first and some other things that are in the steam. So let's kind of go back upstream a little bit. I want to go back up into the steam main prior to the solenoid valve. And if you want to look at this diagram from left to right, we're bringing our steam in at a specific pressure, and the steam would be exiting that flange area on the right-hand side. And again, all the steam wants to do when it comes in contact with a cooler pipe or cooler surfaces is condense back into liquid. The other thing that's in steam are some non-condensable gases that must be removed, as obviously they can lower the temperature of the steam and cause some other issues. But in this diagram, you see here a drip leg is what we call it, and a steam trap upstream of the entrance into the steam space. And steam traps typically work on a principle of differential pressure. So as long as that inlet pressure exceeds the outlet pressure, liquid condensate is removed from the system and steam is trapped upstream of the trap. So we call it a steam trap, but it's really an automatic valve that removes liquid and keeps steam upstream and make sure that it's nice and dry. So the first thing we really want to do is to make sure we have a nice drip trap upstream of this of the solenoid valve. Secondly, there's an air vent, as you can see in the upper sort of right-hand corner of the diagram there. And the air vent obviously is going to remove any non-condensable gases that get trapped in the system. And there are always non-condensable gases. And obviously those folks that have thermal pane windows know that gases can be a very effective insulator, because that's what's between the two panes of glass in your between your windows. So those two things, removing the liquid, removing the air, are obviously paramount. Some steam traps at lower pressure will do both of those two things as well. So we want to make sure that that is the very first thing we do on a system like this. Okay, so the next thing we want to do is talk about what is steam quality. And the steam quality commonly refers to the amount of water in the steam. And I'm going to kind of expand that a little bit to the cleanliness of the steam. And obviously we'll get into that in a second, but also the presence of non-condensable gases and the presence of superheat, which I'll talk about in a second. But steam quality, as it refers to dryness, is a calculation of the mass of steam divided by the mass of steam plus the entrained water. So that'll give you a fraction less than 1, and obviously 1 would be an ideal, quality, dryness rather. But in a fraction less than that, anything greater than 90% is typically what most OEMs are looking for as far as steam quality going into their system. The other side of this, obviously, is the percentage of non-condensable gases within the steam volume. And those folks know about the Bowie-Dick test. Enables you to ensure that you can measure that those non-condensable gases, because what you don't want are low your sterilization loads being insulated by gases that would prevent the steam from penetrating, the heat from penetrating the instrument pack to make sure that it is sterilized. And finally, we're not going to talk too much about this, but steam quality also refers to in the standard the presence of superheat. And if you talk about when you reduce pressure going into a specific space, there is a higher sensible heat in the steam. So there is the ability to produce some superheat, although it's generally not as big of an issue as some of the wetness issues we have, or non-condensable gases that are getting into the chamber. So I'm not going to talk too much about that. It is in the standard and some ways to mitigate that, but we're going to really focus on the dryness, non-condensable gases. And the last thing we're talking about is dirt particles in the steam. So you think to yourself, well, steam should be clean. Where does the dirt come from? Well, the pipe work that you brought your steam up to the sterilizer is made of iron or steel, or could be stainless steel, and there could be some pipe scale that flakes off over time, and some other debris that gets caught up into the system. So we really don't want that entering our sterilizer space either. So we're going to talk about really moving the water, the non-condensable gases, and the dirt particles from the stream before it enters the steam chamber. So let's go back to non-condensable gases for a second. And non-condensable gases really can't be liquefied in compression under normal sterilization conditions. So we're talking about air and carbon dioxide typically. And these two gases, or any gases really, don't have any latent heat. So even if they have the same temperature of steam, they can't heat or provide no heating effect. And so they're really, they're not something we want taking up molecular space inside our steam chamber. They also can collect as a film on surfaces and act as insulators that'll inhibit the flow of steam to whatever we're trying to sterilize. And of course, they also can lower the steam temperature. They are terrific insulators. And so removing those gases, specifically by the use of air vents and some other things we'll talk about, is really important. When we look at trying to be as efficient as possible, these are very simple actions we could take to remove the gases prior to going into the system. It's funny when hospitals start up and shut down routinely, people don't understand that sometimes they'll isolate a steam main upstream of a sterilizer. And of course, obviously over time, air and things are going to get into that steam main. And that's really the first thing that is going to be entering the steam space. And it may increase the ability, or may increase the time period required to heat that system up to its proper temperature. So we don't want to make sure those gases get out. And the easiest thing to do is put an air vent, as you see in the picture, prior to going into the to the steam space, so that all those gases just get removed. And that air vent is a thermostatically controlled device. So when steam temperature gets close to the steam temperature, it closes off by use of a bellows that is temperature reactive. Okay, so the picture you're seeing down there in the corner is what's called a wet pack, and it's a no-no. In fact, that would probably be rejected. So what we see here is excess moisture, droplets that are present, gets onto the porous material and provides an uneven temperature distribution. And so if something like that would come out, would probably definitely be rejected by hospital staff and have to be unpacked and then repacked. So it really is a nuisance at the very least. But we have some smaller institutions that will have to cancel a surgical procedure, and that could be a revenue impact. And we've a few years ago we had a conversation with a smaller community hospital that so it said that the financial impact of something is inane as a wet pack would probably be $35,000 to $40,000 if they had to cancel a procedure. So whatever the case is, it is either a nuisance, but it is a time-intensive issue, having to reject that pack and then repack it and perhaps even cancel a procedure. So obviously it is a problem. The load should be dry before the sterilizer door is opened, and the presence of water will basically compromise the sterility of the product. And how does that happen? Well, as soon as the door opens, the air rushes in, and this is sterilized packages are electrostatically charged, so immediately tracks dust and particles, and those wet points, no matter how small, can lead to contamination. At the very least, again, we're talking about reprocessing that pack. So we're talking about time, energy, cost, and delays that are going to keep this system, from functioning normally. And system being the operating room procedures. We typically, when we talk to people who have pain in this type of area, the folks that are managing the operating suite, many of the head nurses are, this is usually the first thing they talk about when we ask them what's your pain, and if they do have issues with their sterilizers, this is number one. So it just is a hassle for them, and hopefully, again, the two best practices we're going to talk about are really going to mitigate but not completely eliminate some of the issues we're talking about here. So in best practices, first off, let's talk about installing that drip trap upstream of the sterilizer. This is just a representation of a typical drip trap. And starting from left to right, the station is an isolation valve. Next piece, that gray piece there, is a strainer with a blowdown valve. And that blowdown valve is very important. A lot of times they're not fitted, but the blowdown valve allows the strainer to be evacuated, the dirt to be evacuated on a routine basis once every 6 months is all it really needs, because we're talking about larger chunks of material that are going to end up in the strainer. We have a union going into a steam trap, and second, after that, a union, and then we have a downstream isolation valve with the yellow handle, a check valve, and of course, at the very end there, a blowdown valve for cleaning any dirt out of the system. Probably we'd use one upstream of the. Let me just get this here. Right in here too, we probably could use a blowdown valve here as well, but just a routine basis, so we are able to clear debris and dirt that settles into these legs here as well. This is a sort of a high pressure representation of a drip trap. As long as we have an isolation valve, be it a ball valve here or something like that, just so we have a way to isolate these systems and then, if need be, replace or repair this device inside. This trap in here is what's called a thermodynamic type of trap. It has one moving part. Most traps have a few moving parts in them, but this is a pretty robust character, and pretty much removes most of the debris or most of the condensate that's going to be in the system. Okay, so secondly, next best practice would be looking at installing a separator and filter station upstream of the solenoid valve going into the sterilizer. Now, there's steam flow coming from left to right. We're coming into an isolation valve, and our ball valve would be sort of, our solenoid valve would be down here on the right-hand side of the diagram. So our steam flow is from left to right. We have an isolation valve. Again, another strainer. We're kind of looking at reducing the big particles, taking them out of solution, and then increasing the filtration as we move down. So a strainer is absolutely essential to take out the large pieces of pipe scale. Secondly is a steam separator. Now this is a hollow-bodied device with a series of impingement baffles, and we're forcing the steam to change direction violently as it passes through a series of impingement baffles inside. And steam does so easily. Steam is a gas, and it moves quickly through a through those baffles and exits out the other side. But any entrained water droplets or dirt are going to fall out, hit the impingement baffles and fall out through the bottom of this device and through a steam trap. So typically we're able to dry the steam out, removing water droplets up to about 98% dryness fraction by the time it leaves here. And we're able to remove particles through the separator down to about 10 microns in size. So that's a pretty good, any dirt that's still in solution down to 10 microns can drop out through the system and will be removed by the steam trap. The next device is a steam filter. This happens to be a 316L stainless steel housing with a sintered steel element inside. So this particular device will take particles of dirt down to about 2 microns in size, and any liquid or any other, well, mostly liquid or inert gases are going to be taken out of solution through a trap at the bottom. What's not being shown here is typically we like to see an upstream gauge, pressure gauge, and a downstream pressure gauge here. The reason for that is we can see the ability of this screen inside to be clogged. So if there's an excessive pressure drop, we can see that in the downstream gauge. And now we know it's time to remove the filter and change it and have it clean. So most customers that use these on their steam sterilizers will have 2 filters, one installed in the housing and then one on the shelf. And once the differential pressure is excessive, they will isolate the system, remove the filter inside the housing, replace it, and then send the old filter out to be cleaned, usually by ultrasonic methods. Finally, we have a isolation valve downstream. And typically, in this case, we like to see, stainless steel, 316L stainless downstream of the of this filter, just so that we don't get any issues with electrons changing between dissimilar metals. So these are typically not found by installed OEMs. So OEMs are not going to include this. They really want a high quality, or assume that you're going to have a high quality product of steam going into the sterilizer prior to operations. So if you read some of their literature, that's really what they're relying upon those that install these systems to do, is to create a environment where the quality of steam is pretty high, 90% or greater, before going through their system. So that's one assumption that a lot of folks are not aware of. And one of the things that we would like to do is to kind of point out, hey, this is a good way to just make sure that all your steam is of high quality going into the heat change portion of the sterilizer prior to touching the wet pack. And again, these are a lot of times retrofitted, and they can be ganged up. So if you have a series of 4 or 5 sterilizers in an area, you could kind of use one of these filter stations, or split them up into smaller loads. But you really do need to treat that steam prior to getting into the steam space. The other thing I didn't really talk about, again, was the superheat portion of the steam quality. And again, that is something that I'm not going to dwell on too much here. If you're interested in that side of the quality equation, you can look at the standard, again, the ANSI or AAMI ISO 17665 standard. But that is a function, again, of that pressure drop, that where you're getting excessive sensible heat cross into your downstream steam, which raises the temperature of your steam past saturation level. And typically speaking, we don't see that lasting very long. It's if you do have a excessive pressure drop, then it could be an issue. But I would refer you to the standard just to make sure that you understand the issues there. I wanted to be respectful of time. I know this was kind of a short presentation, but I was I was kind of told that to keep it tight. I wanted to open it up to questions if you guys want to, if that's okay with you. Beth or Rose, do you what do you want me to do? Stop sharing my screen, or how do we want to do this?
Yeah, absolutely. Yeah, go for the questions. Feel free. Yeah, perfect. Thank you so much. That was awesome. Very informative.
Do we have any questions?
I guess I'll ask one.
Go ahead.
How often do you see the steam separator put on upstream of the autoclaves or the sterilizer? Is it, most of the time, some of the time? I'm just curious if the steam quality is bad enough in plants typically where you actually need that.
Yeah, that's a good question, John. Thank you. So we've seen some issues where the steam is hot, very poor quality, and it generally there's a problem before somebody takes the action to install the filter station. So unfortunately, nobody ever says, "Hey, I'm going to put some sterilizers in. Let's put some steam filter stations in first." It's always retrofitted, and it's usually after a problem with sort of chronic wet pack issues in the sterilizer. So I would say 20 to 25% of the installations, and we're talking about one customer we have is on a district heating loop, and the steam is of excellent quality leaving the cogen area, but by the time it gets to where the sterilizer is, which is about, oh God, I'd say about 1,000 feet of horizontal run and some changes in elevation, we've got some pretty nasty steam coming out. So it generally, they had to do something and ended up putting steam filter stations in.
Mark, it looks like there's some questions in the chat. Are you able to see that?
Let's see here. Oh, here we go. Okay. So Greg said, perhaps a guideline review on drip leg diameter versus steam pipe diameter. That's a good question. And going back to the screen with the drip leg, what happens to the condensate? What happens to the condensate? I guess after the thermostatic valve, or I guess we're talking about the trap. Okay, so bear with me a second here. I'm gonna go back and see if I can get an answer to one of these questions. So I'll answer the second one first, just because it's an easier question. So the condensate typically goes back to the condensate return. So condensate is extremely expensive. You spend a lot of money to put chemical and energy into the condensate. So what we really want to do is to use that and reuse it. So that would be you'd want to pipe that back to your condensate return. And let me share my screen again. Having some issues here. Okay, let me know if you can see this.
Yes.
Okay. So this is basically a best practices for drip trap assemblies. And these are located, we say every 100 feet or upstream of valves or bends in pipe. Anytime the pipe changes direction, we want to eliminate low points in the system. So this is a sort of a best practice, and the diameter of this, what we're calling the drip leg or dirt leg, is to be equal to the steam main diameter for steam mains up to 4 inches. So if you have a 2-inch main going to your sterilizers, we want this diameter of the leg to be 2 inches in diameter. And then of course, if your drip leg diameter must be half the size of the main, greater than 4 inches, but not less than 4 inches. So that would be the diameter, and the length we'd like to see typically for automatic startup to be 28 inches minimum. That ensures that you get enough volume to take the liquid out of the system and allow for a little bit of dirt collection down at the bottom of the leg. And then with supervised startup, typically, which is never, we like to see that to be 1.5 times the diameter, but no less than 8 inches. So this is just some rules of thumb for for using this. And if you like, I can make this available to you folks for your use, or you can check out our website. But that would be that's just a basic standard rule of thumb for that. How about any other questions?
I think there's, oh yeah, I think you got it all right. Yeah.
Just out of curiosity, does anybody have issues with wet packs or rejected packs of instruments that are supposed to be sterilized? Is that an issue in your facilities? Anyone? I guess everybody has perfect steam. That's awesome. Okay. It doesn't appear that we have any other questions.
Okay, good stuff. Does anyone have anything else they want to say, bring up, questions? Otherwise, we can close early. And remember, we are looking for a sponsor for in-person for the next meeting on September 20. You can reach out to Beth or I.
And also, real quick, don't forget to register for the Northern California Seminar on October 20th in Fairfield. We want to see you all there.
Where in Fairfield is that?
Fairfield Marriott.
Okay.
All right. Thank you, everyone. Thank you, Mark. Look forward to seeing all of you in September, and I hope you have a great rest of your week.
Thanks, gang.
Thank you.
Thank you.
Thank you. Have a
Bye.
nice day.